Hello, welcome to today's class on hypothesis testing fundamentals. So this is one of the key statistics topic that is tested frequently on all the steps of the USMLE exams. Let's begin. So we are talking about hypothesis testing fundamentals. And as you know, before we begin any kind of research activity, it is vital that we know what test we're using to get significant evidence-based results out of the test that we're going to imply. So to begin, what are hypotheses and what is hypothesis testing? Now, the definition of hypothesis testing is that we use a statistical technique to evaluate mutually exclusive statements that might exist about a population to be able to determine whether that statement is actually supported by the data that's being analyzed. What does that mean? Now, of course, it's super important to be doing this because it's basically the essential question that you're starting your research with. And it drives every kind of research, not just in medicine, but also in like the food technology industry, the pharmaceutical industry, and even other big data companies that work on all kinds of population statistics. So delving into understanding hypotheses. So the basic idea is if I have a research process, I have to think of a question. The question could be, hey, is smoking related to lung cancer? Or does this drug A that's being discovered or being processed or is under trial really affect the recovery period of a disease? So I start with a question and I give an answer that says, no, there is no relationship between the studied variable and its effect on the research itself. So this statement is called a null hypothesis and is signified or symbolified as H naught. So as you can see, H naught is the null hypothesis that says that it's a default agreement that there is in fact no relationship between the studied variable and its outcome on the studied question. And what is an example? It could be that the drug that we're saying it has no effect as you compare it to a placebo, and in fact would have no implications if used clinically. It could also be said that, okay, a risk factor like age has no relationship with increasing incidence of hypertension in men above 50 years of age. So to be able to reject that, we need an alternate hypothesis. An alternate hypothesis is the contradictory statement or the counter argument of our null hypothesis that says that, of course, there's a relationship. There is a significant relationship between the studied variable and its effect on the outcome being studied. So this is the researcher's belief. And this prediction has to be supported by evidence. And when we get the evidence, we reject the null hypothesis and accept the alternative hypothesis. And that is the very essence of statistical significance testing. Now, we talked about how alternate hypotheses could have examples. Let's talk about what kind of testing are involved. And this is the core key concept being studied today. So we have n number of tests and they sound quite complicated. I'm sure we've heard of like student t-test and ANOVA and chi-square, the really famous tests. There are also tests that sound so fancy and are difficult to remember what they mean. So let's break it down to a very simplified version. So when we talk about variables being compared, they can either be numerical, like the means, which are the averages of the population, or they could be categorical, that we're seeing proportions or percentages. So when we have means, we can either have two groups being compared to, like the mean number of patients having hypertension in the group of men versus women. So those are two groups with their means being compared. And the kind of test that we would need to be used in that situation would be a t-test. And if we have more than two groups, if we are studying the effect of age in obesity in different pediatric groups, and we have groups like children age 0 to 10, 10 to 15, and 15 to adults, those are three or more groups of population and their means being studied, we would use something known as the ANOVA test. While if you're talking about proportions or percentages, if we have a smaller population size, we use something called the Fisher's t-test. And this, if expanded to a much larger population, the chi-square test comes to our help. So speaking of the first test we have on here, the student t-test, we basically compare the two means of independent groups to see if there is a statistical difference between the two groups at all. And this is also a very commonly used test. Next, we have what is known as ANOVA, which we said is used for 3 or more groups for comparing their means, and it stands for analysis of variance. For your percentages or proportions, you have the smaller population, Fisher's exact, and the larger population chi-square testing. And our chi-squares are essentially looking at a particular value called the p-value from the analysis. And that is a numerical decimal value that tells us, is the analysis showing significant results? And the cutoff for the p-value is known as 0.05. And if the p-value that is generated out of the research says it is less than 0.05, then you say, aha, my statistics show significant evidence that what I'm testing is actually backed up by data. And then you can reject the null hypothesis and accept your argumentative alternate hypothesis. Whereas if your p-value is greater than 0.05, you say that your research is not significant and you will have to hold on to what you know as your default or your null hypothesis. You also have different chi-square variables, the degrees of freedom, and the other aspects which we're not talking about just now. Now, we have something known as the Mann-Whitney test, the Wilcoxon-Stein rank test, and the Kruskal-Wallis testing. They're also like the t-test and the ANOVA, that they're used for numerical values, but they're not for distributed data that it follows a normal distribution or a bell-shaped distribution. It's for skew data. And you also have the Shapiro-Wilk test or the Kolmogorov-Smirnov test. You don't need to know what they are, just need to know that they're not your usual data. It's for more different or skew data that you use it. And then you have the Friedman's testing, which also compares more than two groups, but for data that is not normally distributed. And last but not the least, we have your Pearson's correlation coefficient. And here we draw the data as points, and the plotted points are seen if they are following a sloping pattern, whether the dots are all towards each other, and if they have an up or down slope. And it could also be a situation where they have no correlation. That is, all the data points are scattered, and you cannot draw a line that intersects all these, or all the points are close to that line. So if there is no trend, there is no similar pattern of the data points clustering, we say there is no correlation between what is studied on the X and the Y axis. If they are correlated, is it a negative or a positive correlation can be determined based on the slope of the line that we draw towards which the points are clustering. A positive R value here, and R value is known as the slope. If they are sloping downwards, you say it is a negative slope with a negative correlation. And if you have a positive slope, you say it's an upward slope with a positive correlation. So an example would be, let's say, smoking and hypertension would have a positive correlation, or you can have exercise and atherosclerosis having a negative correlation, which is in fact translated as a protective effect of the risk factor being studied. So this was our basic types of statistical testing. We also have errors in which we can say, was the study done correctly analyzed? Did the test that we choose give us the right results? And what would that be? So like we said, if you have evidence that your research actually made sense and there were significant results, then you should dismiss the null hypothesis and accept the alternate hypothesis. Now, a type 4 error would be when you null hypothesis is incorrectly rejected, which means that there is a false positive information that you really thought that there was an effect there wasn't evidence of change brought out by the variable being studied, but in fact, there wasn't. So the null hypothesis was inaccurately dismissed. That is a type 1 error. And this can have a lot of implications and could be that you're actually bringing into effect a treatment or a procedure, a drug that not exactly has any clinical evidence, but because of the inaccurate study is being accepted into clinical practice. And this could have really bad implications on the population that's being affected by the implied medicine or the trial or whatever. Whereas the type 2 error is that there was an effect by the alternate hypothesis, but that was overlooked. And in fact, the null hypothesis was held on to. So this is a false negative kind of error, and this is called a type 2 error. Now, this can also result from a wrongly conducted or wrongly analyzed study. And here, what the effect would be is that you missed an opportunity to use the research and the analysis to take up or accept the new drug or trial or procedure, and you just held on to the already status quo. So that would also impact public health and prevent them from utilizing these new researches, beneficial treatments, and being a more robust healthcare system. So that was the basic about the errors, and we'd have to balance the type 1 and the type 2 errors by effective and robust hypothesis testing and making sure we use the right test for the right kind of data being studied, and also pay importance to the variables that we are analyzing in that study. So that was all about hypothesis testing fundamentals, and hope to meet you guys again about a new concept. Thank you.